before I do any questions, posted a bunch of grades on Blackboard at this point. If you've got a -1, that means I haven't graded it yet, or I still want to see it. Blackboard has this automatic color coding that I have no control over. I played around with it a couple of years ago, and I can change the color coding on what I see, but not what you see. So here's the Blackboard thinking. If you got a C on something, you got 2 with a maximum of 4. So it's going to show you 2 out of 4. Blackboard thinks, oh, you got 50%, that's failing, and it marks it red. It's not failing. If you got 2 out of 4, that's C. So it just doesn't seem to want to break itself of someone else's system. So I've had students panic in the past because they think they've failed all these assignments when they hadn't. All right, any questions? Okay. Last thing we did when we had class. We did that, and then we got into moment of inertia and
When are we gonna see like our tests and stuff like that?
today. Yeah, need to talk to some people, but during lab line stuff back. Or as you're leaving, I will hand it to you. I haven't quite worked out the logistics yet. The only ones who would understand this reference probably are my former students. So, what I'm talking about is torque. Now, what does G2 Kombucha have to do with that? That's something that you can figure out later. Pardon? Which, that's the character's name or not the character? Yes, it was. Do you remember the show?
My granddad used to watch it. I can't remember the name, but I remember that name.
You're the second. I had another student who knew the reference because his dad had told him about it. So I think that we've now found 3 people who watched that series.
I can't remember the name of it.
A Man Called Slow.
That's right. That's right.
One of Robert Conrad's many
That's right.
failed series. All right, that's nice of them. Is your grandfather still around?
No.
Ah. All right. All right, so torque. If I push on this object, I apply a force, it might accelerate or might not, depends on how much force I apply. But we now are getting more sophisticated because we know not all things will move like that. If I have, right now I'm applying a force to it, it's in equilibrium, but if I apply a force here, what's gonna happen?
As you push up, it'll lean down.
Okay, otherwise known as rotate. Your description was more thorough. So torque is the thing that causes things to rotate. It is an influence that might cause angular acceleration. Sounds a whole lot like the very vague definition of force. Twist or turn, I need to put out something else about that. All right, so let's try to think about what actually would cause something to twist or turn. Now, it's really helpful to be in a classroom where the door swings inside for this, which we don't have. So that doesn't turn, those doors you can't see, so we are going to have to improvise. We have a door. So, if I want to close this, how should I push on this to get it to close as efficiently as possible?
Just push on. Like in.
Wait, that didn't work.
Push, pull it in.
Pull it in,
Pull it towards you.
pull it towards me. That didn't quite work either.
Adjust the straps, adjust the two that are here, the two flaps.
Right.
And that flap right here, you just pull it towards you.
All right, so- Would it be helpful if I did it from that? All right, so where should I push on this thing to close it?
Push on the middle.
Push on the middle,
So towards the end of the end there,
towards the end,
yeah,
not the middle?
no,
Why the end?
because that's what's gonna end up closing it with the box. That's the last part that's gonna touch the box.
Okay, so I'm gonna push on the end,
Not right there, like,
that's the end.
the end of the. Okay.
I once did something similar, for a different purpose, I did something similar about how to tie shoes. That was entertaining. All right, so
So the end of the flap right here.
the end, that is the end of the flap.
No, that's part of the door. Because you're gonna have to push that one in order to create the door.
All right, so you're talking about this surface here.
Yeah,
Push on this surface, not just the end,
yes.
right there. All right, so obviously, all of us know how to close a door, I'm assuming. Let's think about what affects how efficiently I close this thing. So let's go to this suggestion of pushing on this surface down at the end. Just because it's bent right there, I'm gonna pick this spot here. If I want to close it, why is it not closing? I'm pushing on the end. Pardon?
You're not adding enough.
So in order to close it efficiently, I need force matters, the amount of force. And the direction I push matters. And how far away from the pivot. So distance to pivot. Probably axis of rotation is a better word than axis of rotation. So we need some sort of formula that can encapsulate these three ideas into one thing. And you're in luck. We have such a formula. First off, the symbol for torque is a tau. Now, first off, this distance to the pivot point has a name. A moment arm or a lever arm. I think Hewitt calls it the lever arm. I typically call it a moment arm. They're used interchangeably. And typically the symbol used for that is an R with a vector. Put that up here first, R. And since it's a vector, it has a direction. So the direction is from the axis of rotation to the point where the force is applied. So when I apply the force here on the tip, on the edge, I have a very large moment arm, but obviously not having much torque, it's not doing much in way of closing this lid.
Is that arrow pointing to the T with the vector?
Yes, that's just the letter tau.
Okay.
It's the symbol that we use for torque. The amount of force matters, so we'll throw that up in there. And then we need to multiply them. And of course, it's not as simple as just multiplying two numbers. It is specifically a cross product. So we have talked about the direction of angular velocity. As this spins, what's the direction of angular velocity? So either we haven't, or people have forgotten, or people are just being quiet. All right, how would you describe the direction of this? Going that way?
Spinning clockwise.
All right, so you got spinning clockwise there. Trouble with pointing that way is this is going that way and that's going that way. People typically look at the top though. Clockwise, I would have said counterclockwise.
Counterclockwise, one of the two.
It's counterclockwise from your point of view, or clockwise.
Oh, yeah, from our point of view, it's clockwise.
All right, so physicists and mathematicians figured out, hey, we gotta do better than that, because imagine the description of, it's rotating clockwise if you're standing in the middle of the room, but if you're standing to the board facing to the back of the room, it's counterclockwise. That's a lot of words that we don't like writing down. So they came up with a system known as the right-hand rule. Now, who's left-handed in here? All right, just want to point out, it's not the dominant hand rule, it is the right-hand rule. I've had, yeah, that's probably the biggest mistake is the left hand that people make is using their left hand to come up with the direction when it's the right hand. All right, so we have an axis right here. The axis in this case is not moving at all, and it spins around it. So in the right hand rule, the thumb is going to be the axis. So the thumb, so since the axis is going this way, the thumb either points towards me or towards the back of the room. Now the fingers are going to curl. They naturally will curl one way around your thumb. So as it rotates, I want to point my thumb in the direction so that my fingers curl in the direction of the rotation. So in order to do that, my thumb has to point towards the front of the room, so my fingers curl in the direction of movement. The thumb is the direction of the angular velocity. So the way that the mathematicians, physicists would describe this is the angular velocity is to the front of the room. That way, if you know the angular velocity is to the front of the room, it doesn't matter where you're standing. Towards the front of the room, that's the direction, point my thumb in that direction, and so it's spinning like that. And you can get away from this clockwise, counterclockwise thing. Now, when I was first doing physics, I got confused by this because I kept thinking, all right, nothing's moving towards the front of the room, nothing's pushing to the front of the room, this doesn't make any sense to me. And it's just a convention for determining direction. It is not, there's nothing actually going towards the front of the room, even though we say the angular velocity is towards the front of the room, we are not making any claims of something physically moving to the front of the room. It's just a way of just expressing something that's rotating. So if I close that door, what would be the direction of the angular velocity of the door?
Thumb facing the sky.
All right, I heard two things at once.
What is that back wall?
You're staying towards the back wall.
No.
In the case of the door, what's the axis of rotation? All right, the head. You did your pencil up and down.
The hinge would be the thumb facing the sky.
Facing,
Thumb facing the sky.
it would be facing the sky. Because my axis is vertical, so my thumb's either gonna point up or it's gonna point down. The door, when it closes, rotates this way about the axis, so my thumb has to point up. When I open the door, my thumb has to point down. So the angular velocity as the door closes is up, it's down as it opens for that door. So, let's bring it back to torque. When determining the direction of torque, it is a vector. When determining the direction, well, we're going to be doing a right hand rule. So, if I've got a door right here, sure, and I apply a force like this, so I'm pushing on a door, think of an overhead view. R is a vector from my axis of rotation to where the force is applied, that's R. Well, first off, which way would that force cause the door to rotate? What would be the direction of, if that's the only, I got a hinge right here, this is the only thing exerting torque on it, causing it to rotate, what would be the direction of the rotation? Yeah, right hand.
Long facing the back a little.
Yes, it would cause it to rotate like that, back of the room. The torque is to the back of the room. The other way that you look at it is you draw the two vectors, R and F, put them tail to tail, and you want to curl your fingers from the first vector to the second vector. So since R comes first, I put my hand in the direction of R. I got 360 degrees of freedom here, but I want it so that when my fingers bend, they bend towards the quickest way to the second vector. So if R is this way, my fingers bend that way to the second vector, my thumb points out. So in this case right here, my torque is out of the board, which we'd symbolize by a dot. We've done 3 dimensions. The dot here, for some look of recognition or non? No, okay. Dealing with I hat, J hat, easy enough, left, right, up, down typically. But now we're into a 3rd dimension here, we need to somehow express that. And so they go to the dot and the X in terms of direction. This has nothing to do with dot product or cross products, just they're using the same letters. The dot means out of the page or out of the surface from the viewing point of view, and this is into surface. And the memory trick that is often talked about is the arrow. If an arrow is shot at you, you would see the point. So if it's coming towards you, it's a point. If it's going away from you, you see the feathers. And I know arrow feathers are not like that, it's just a memory trick. So let's try to get more questions before we make it more sophisticated.
What does the red dot have inside of it? Is that what letters?
What is that?
You know, next to it, is that just a dot?
That's just a dot.
Okay, I thought it was some letter or something.
No, no, just a dot. It's the arrow pointing out of the board.
So if the handle was, the force went this way, would the answer then be into service as far as?
Yes.
torque?
And sort of on that note, when we dealt with dot products before, if I had A dot B, that's the same as B dot A. That's supposed to be an A. Math people, they say commutative property holds, doesn't matter the order in which you do a dot product. Cross products, it does matter. R cross F points out of the board, F cross R points into the board. R cross F does not equal F cross R. So order does matter. Other questions before we make it more sophisticated or to look more difficult? F cross R. Sorry, R cross F now. R cross F. Put your hands in the direction of the first vector, R. And you want your fingers to curl towards the second vector,
Don't
which is
face
coming out.
Front,
Pardon?
don't facing front. Don't facing the front of the class.
Oh, face the front? It is not. How'd you get that? You put your hands in the direction of R. Which way is F facing? The dot. Which way does the dot indicate?
Out of the surface?
So when you just said it?
Out of the surface?
Yeah, out. So F's going that way. R is that way, F is that way. So you going that way?
Yeah.
No, and here's a hint, is that when you do a cross product, the result is perpendicular to those two vectors. So R, F is that way. The torque would be up. So F's coming out that way. R cross F. Now, great. We got some hand motions here to describe the direction, still working on it. What about a number? If R is perpendicular to F. So if they're perpendicular, the magnitude of the torque, so just the magnitude, not worrying about the direction, just the magnitude is just R times F.